Now the next topic is difference between heat and temperature. Now the first point of difference is their meaning, isn't it? Or definition. Like heat is a form of energy which flows from a hotter body to a colder body when the two bodies are brought in contact. Temperature is the degree of hotness which decides the flow of heat when the two bodies are brought in contact. Now that was the difference in their meaning. Next one is the SI unit of heat is joule and the SI unit of temperature is Kelvin. Next one, heat is measured by a calorimeter. It's a vessel with which we measure heat, and you all know. So which instrument measures temperature? Is the thermometer. So it is measured by a thermometer. Now the next point of difference is heat depends on mass. Alright, now let's say you have this much of sand here, and in another body you have this much of sand. Okay, now if these two are placed in boiling water, which will acquire more heat? This vessel will acquire more heat. This sand will acquire more heat than this. So heat absorbed by this sand will be more than this because it has more mass. Okay, that's why heat depends on mass. But the temperature does not depend on mass. So let me explain you like this. Suppose you have got this much of water and this much of water boiling. Okay, so we have got this water boiling and this also is the water that is boiling. Okay, here you see more mass of water and here you see less mass of water. So which of these two will have more temperature or will show more temperature? None of these two will show more temperature. These two will have the same temperature of 100 degree Celsius. So both of these two will show temperature 100 degrees Celsius and 100 degrees Celsius. What does it mean? Temperature does not depend on mass. Heat is the cause and temperature is the effect, because heat changes the temperature. Next topic is factors affecting the amount of heat of a body. Okay, let me take you back to the topic on calorie. So from the definition of calorie, you mean that if we take 1 gram of water, okay, and to raise its temperature by 1 degree Celsius, you need to supply some amount of heat, and that amount of heat which is required here is 1 calorie, isn't it? That's it. So that's the definition of calorie which we have already done, and I think you have understood it also. Now let me take 2 grams. Okay, so this is 2 grams of water out here. So in order to raise its temperature again by 1 degree Celsius, what will be the amount of heat required? Will it be more than this or less than this or equal to this? Obviously it should be more than this. Since the mass has doubled, the heat required should also be doubled. So in this case you require 2 calories of heat. Okay, so you see that as the mass increases, the amount of heat also increases. That's why the first factor affecting the amount of heat of a body is the mass of the body. Okay, and so more the mass, more will be the amount of heat. And mathematically we write this Q, that's the amount of heat contained in a body, is directly proportional to mass, where Q is the amount of heat and M is the mass. So it means that more the mass, more is the amount of heat contained in the body, and less the mass, less will be the heat contained in the body. Now factor number 2. Now to understand the second factor, let me take the same example of this calorie. Okay. Now this is 1 gram of water. For its 1 degree Celsius rise in temperature, it requires 1 calorie of heat. No? Now I'm taking the same amount of water, which is 1 gram. Okay, but I want to increase its temperature by 2 degree Celsius. So here the rise in temperature was only 1, but here it is 2. So there's more rise of temperature, isn't it? So what does it mean? The heat required will also be more in this case, isn't it? So since the temperature is doubled here, keeping the mass same, the amount of heat will also be doubled. In this case, instead of 1, 2 calories of heat will be required. Alright? That's why we say the amount of heat contained in a body also depends on the rise in temperature. Okay, so it depends on difference of temperature, and that is denoted by delta T. Okay, and you just saw that more the rise in temperature, more will be the heat required. So they are directly proportional, isn't it? That's why we write Q is directly proportional to delta T. More the rise in temperature or the difference in temperature, more will be the heat contained in the body. Okay, so let this be equation number 1 and this be equation number 2. All right. Now let me take you to the third factor. Again, back to the same example, and this is your water, no? Now if I take 1 gram of any other substance other than water, okay? So this is any substance. It can be gold, it can be silver, it can be iron, aluminum, any substance, or sand also, any substance other than water. Now for its 1 degree rise in temperature, look at this, both have the same mass, and in both the cases the rise in temperature is the same. Now you think, will the amount of heat required in this case be the same 1 calorie? Answer is no. Although they have the same mass and the same rise in temperature, okay, the heat required in this case will be different from this one. So what does it mean? The heat required in different substances, okay, will not be the same. It will be different in different cases. Okay, so it actually depends on the nature of the substance. So the third factor on which the amount of heat of a body depends, okay, is the nature of the substance. All right, so this is it. So these are the 3 factors on which the amount of heat contained in a body depends. Now to get the formula, the mathematical formula for the amount of heat contained in a body, we use the 2 equations like this. So Q, that's the amount of heat, depends on mass, that's directly proportional to mass, and the amount of heat is directly proportional to the difference or the rise in temperature. No? Now we are going to combine these 2 relations, okay? And this is the concept for combining 2 relations, 2 variation relations. Now suppose A is proportional to a quantity B, and the same quantity A is proportional to another quantity C, then what we do, in order to combine, we do it like this. So it is neither addition nor multiplication, okay? So A and A will not make 2A or A square, we write A only. And proportional remain as proportional, and we multiply these two, okay? So B into C. So this is called the theory of joint variation, and we'll be using this particular concept in so many cases in physics, okay? And this is one of those different cases. Now, according to that relation, Q and Q will remain as Q. It is proportional. Now what we need to do with these two? Multiply. So it's M into delta T. And you must be knowing that. So when you replace this proportional sign by equal to, you have to put a constant, where K is the constant of proportionality. Alright? B into C. Now let me apply the same rule out here. Q is equal to some constant into M into delta T. Now that constant, okay, K is a constant of proportionality, and that constant in this case is written as C, which is known as specific heat capacity. So I will take this topic in detail, okay, after completing this particular mathematical relation. All right. Now, so this K is now C, which is the specific heat capacity, into M into delta T. So this is the formula for the amount of heat contained in a body. Okay. So depends on mass, depends on the difference of temperature, and C is the specific heat capacity, and this specific heat capacity is different for different substances. That's why we say the amount of heat depends on the nature of the substance. That means the specific heat. So our new topic is specific heat capacity, and that is denoted by C. Now to understand the meaning of this specific heat capacity, okay, I will again take you back to the definition of calorie. Okay, so if you understand the definition of calorie properly, okay, you will easily be able to write the definition of specific heat, and hence you will easily understand the meaning of this specific heat capacity. Okay, so again, so this is water, and for that, how much water we take? 1 gram. So in order to raise the temperature of 1 gram of water through 1 degree Celsius, so we can't do this without supplying heat, isn't it? Some amount of heat is required, isn't it? So whatever heat is required in this case, that amount of heat, you all know, is known as 1 calorie. Isn't it? So 1 calorie is the amount of heat required to raise the temperature of 1 gram of water through 1 degree Celsius. Alright? Now, if I replace this by any substance, this is any substance, okay, other than water, or you can take water also, okay. So this is any substance like sand, gold, platinum, iron, aluminum, anything. Alright, and we take its unit mass, okay, we take mass to be unit. It can be 1 gram also or 1 kg also, depending on the system, right? Now, to raise the temperature of unit mass of a substance through 1 degree Celsius, you know, like in this case, this also requires some amount of heat, isn't it? What is required? Some amount of heat is required, isn't it? And that heat in this case, it was called 1 calorie, isn't it? And that heat in this case is known as its specific heat capacity. Okay, so how do you define specific heat capacity? It is defined as the amount of heat required to raise the temperature of unit mass of a substance through 1 degree Celsius. And there is another way of defining specific heat. Okay, we get the same definition. Okay, we get the same definition from this relation also. Heat, as you know, is equal to, okay, I'll write here. Heat, as you know, is C into M into delta T, isn't it? Now, in this case, how much mass we are taking? 1 unit mass. So, M is 1. Okay, and what is delta T? Rise in temperature. Rise in temperature is also 1 degree Celsius. So, if these two are the values, let's put these two values out here and let's see what we get. Q remains as Q. C, we don't know the value of C. What is the value of M? It is 1. What is the rise in temperature? 1. We don't write the unit. Okay, so when we multiply, we get this. So, again, we have landed to the same meaning of the specific heat capacity. So, this also tells that specific heat capacity is the amount of heat, okay, required to raise the temperature of unit mass of a substance through 1 degree Celsius. So, this is the meaning of specific heat capacity. So, the amount of heat is given by C into M into delta T. So, if you are interested to find out the formula for C, so the same relation will give us the formula for C, the specific heat capacity. Okay, so first of all, I'll change their positions. Okay, so when we change the position of both sides, there will be no change of sign, as you all know. C into M into delta T is equal to Q. And what is C equal to? So, we are keeping C here, the rest is to be transposed, isn't it? So now we have to transpose these two terms this side. So into will become divide, no? Q divided by M delta T. So this is the mathematical form of specific heat, and the same formula will give us the unit also. Units of C. Now, first the CGS unit. This formula will give you the units of C. Now, Q means the heat. So, what is the CGS unit of heat? It is calorie. Now, this is in denominator, that means per. Now, what's the CGS unit of mass? Gram. Again, denominator per, and this is temperature, difference of temperature, this per degree Celsius. Or the same thing can be written as this also, calorie per gram per degree Celsius. And the next one is the SI unit of C, specific heat capacity. Now, this is the heat, and the unit of heat is joule in SI. Mass, SI unit of masses per kg, and unit of SI unit of temperature is Kelvin. So, the same thing can be written as joule per kg per Kelvin. So, this is how you write the units also. Now, this is the question. The specific heat capacity of water is 4200 joule per kg per Kelvin. So, the specific heat of water is given as this 4200 joule per kg per Kelvin. Okay. Now, from this, we first take out the different quantities denoted by the units. Now, kg means, per kg means 1 kg. Per Kelvin means 1 Kelvin, or you can say 1 degree Celsius. Okay, the difference of Kelvin and Celsius will be the same, which I told you last time also, no? So what does it mean? To raise the temperature of 1 kg of, where is that? Water, no? 1 kg of water through 1 Kelvin or 1 degree Celsius. How much of heat is required? This much of heat is required. That means 4200 joules of heat is required to raise the temperature of 1 kg of water through 1 Kelvin or 1 degree Celsius. Okay, so the statement means that to raise the temperature of 1 kg of water through 1 Kelvin or 1 degree Celsius, then 4200 joule of heat is required. So this is how we interpret the meaning of specific heat, and this specific heat is different for different substances. Okay, and you have to bear this in mind that this substance, which is very important for our life, isn't it? This substance, water, has the highest amount of specific heat, and that is 4200 joule per kg per Kelvin. Now, to understand the comparative values of the specific heat capacity, let me give you this example. Let's say this vessel has this much of capacity, okay, and there is another vessel. Let's say this is another vessel B, okay. Let this be vessel A and let this be vessel B. You can see in the diagram also, both the vessels, okay, have different capacity but have the same height, no? Have the same height. Now, in order to fill it completely up to this much of height, okay, so how much of liquid is needed? This much of liquid is needed, no? So to fill completely, this much of liquid is needed. Okay, now to fill it completely, will the same amount of liquid be sufficient? Look at the capacity. It will require a greater amount of the liquid, isn't it? Likewise, if we consider these two vessels as two different objects, okay, and if we take this height as the rise in temperature, let's say from here to here the rise of temperature is 1 degree Celsius, and the amount of the liquid, okay, we are considering that amount of liquid as the amount of heat. Okay, now to fill completely, okay, with the liquid, that means to raise the temperature through 1 degree Celsius, how much of heat is needed? This much of heat is needed, no? But in this case, for the same rise in temperature, that means for the same 1 degree rise in temperature, okay, how much of heat is needed in this case? Which is far more greater than this one, isn't it? The heat required in this case is far more greater than this one. Okay, that is the concept of specific heat. Okay, so this vessel has got larger capacity, that's why it requires large amount of heat, a large amount of liquid to fill it, isn't it? Similarly, if we take this as a substance of greater specific heat, okay, greater specific heat means it requires greater amount of heat for the same rise in temperature. So what does it mean? If a body has higher value of specific heat, means for the same rise in temperature, that body will require a greater amount of heat, while a substance which has lesser value of specific heat, okay, requires lesser amount of heat, okay, for the same rise in temperature. Okay, so specific heat of, let's say, copper is 389 joule per kg per Kelvin, and you already know that the specific heat capacity of water is how much? 4200 joule per kg per Kelvin. So look at the values. Okay, it has a greater value of the specific heat capacity. What does it mean? For the same rise in temperature in both the cases, okay, water will require a greater amount of heat, which is 4200 joule, whereas for the same rise, that means 1 Kelvin or 1 degree rise in temperature, copper will require only 389 joule, less than 400, isn't it? So this requires far more greater amount of heat, and this requires very less amount of heat. So that is because of this specific heat. So this is how we compare the different specific heats. Now, another thing which you have to remember about specific heat is, now look at this. Now this example is a very good example for me to explain this particular fact. Okay. Now in between copper and water, which is a good conductor of heat? It's copper, no? But you know water is a bad conductor of heat. And look at the values. Its specificity is more, isn't it? Whereas its specific capacity is less. So what do you have to understand regarding this? More, the specific heat capacity makes the substance bad conductor of heat, and lesser value of the specific heat capacity means that substance is a good conductor of heat. Okay, so heat. Okay, now let's have few numericals based on the specific heat capacity. And your question is like this: 50 grams of a metal piece at 27 degrees Celsius requires 2400 joule of heat energy so as to attain a temperature of 327 degrees Celsius. Calculate the specific heat capacity of the metal. Now in this case, let me first of all write the given quantities. So what is 50 grams here? This is the mass of the metal. 27 degrees Celsius, this is the 27 degrees Celsius, this is the initial temperature, isn't it? So I will write T1 in order to denote the initial temperature, okay? And what is the final temperature attained by the metal? T2 is 327 degrees Celsius. And for that, how much of heat is required? It is 2400 joule. And these are the things given to you. With this, you are asked to calculate the specific heat capacity of the metal, isn't it? Now, we know in the formula there is a term called delta T, isn't it? That's the difference of temperature, either that is rise or fall in temperature. So that delta T, you have to find it here. It will be easier if you find the value right here, okay? Now delta T means higher temperature minus lower temperature. That means T2 is higher in this case, T2 minus T1. So 327 minus 27, that's equal to 300 degrees Celsius. Now we have the values of M also, delta T and Q. We have to find the value of C. And the formula which we know is Q is equal to M into C into delta T, no? Since we have to find C, so I've written this ahead of Q, alright? So From here, what is C equal to? This is Q. So you have to transpose these two to the other side, isn't it? So it becomes, the into will become divide M into delta T. So the rest is put the value, get the result only. C is Q. Q is 2400. At the same time, I'll write the unit also. All right, that is joule. Mass is how much? Now gram. Now in this case, you can express this in gram also. Okay, like joule per gram per degree Celsius also. All right, if you want. Or since we have used joule out here, let us express this in kg also. So it's up to you. You can keep the answer in terms of gram, or you can express the answer in terms of kg also, which I am doing right here. And 1 kg means you have to divide it by 1000, becomes kilogram. So these two get cancelled. 5 ones are 5 20s, so it's 1 by 20 kg. So mass is 1 by 20, no? Into delta T. What is delta T equal to? It is 300. So now little bit of simplification. So these two get cancelled. So 3 ones are 3, 3 8s are 24. And this 1 by 20 is kg, no? So this is per kg. Per this 300 is degree Celsius. And now I'll write the rest of the things out here. So 8 is left. 1 by 20, you have to invert it, isn't it? So 20 comes up in the numerator. So it's 20 joule per kg per degree Celsius, or per degree Celsius. 1 degree Celsius means the difference of 1 degree Celsius is 1 Kelvin, no? So you can write Kelvin also. So finally, the answer is 160 joule per kg per degree Celsius, or per Kelvin also you can write. Now another question based on specific heat capacity. A certain amount of heat Q will warm 1 gram of material X by 3 degrees Celsius and 1 gram of material Y by 4 degrees Celsius. Which material has a higher specific heat capacity? Right? So let me draw the question for you. Okay, let me explain you by drawing the given things. Now this is substance X and this is substance Y, right? So what is given to you? A certain amount of heat Q will warm 1 gram. So this is 1 gram of material X. Okay, so how much of heat energy is supplied? Q. Okay, due to which the temperature rises by how much? 3 degrees Celsius. And in the second case, 1 gram of material Y. So again the mass is same, 1 gram of material Y, and you are supplying the same amount of heat Q. Okay, that rises the temperature by 4 degrees Celsius in the second case. Okay, so you see both the materials have same mass and they are supplied with the same amount of heat, but the rise in temperature is not the same, isn't it? Here the rise is 3 degrees Celsius, rise in temperature is 3 degrees Celsius, and the rise in temperature here is 4 degree more here, isn't it? Now you are asked to find out which of these two bodies has higher specific heat capacity, isn't it? So we know M into C into delta T is Q, isn't it? So therefore, what is C equal to? Q divided by these two, because you have to transpose it. So into will become divided by m into delta T. Alright, so you see the specific heat depends on these three things, okay? Now, for X and Y, Q is the same, mass is also the same, isn't it? The different thing is the difference of temperature. So here delta T is 3 degrees Celsius, delta T is 4 degrees Celsius here, isn't it? So what does it mean? This is in the numerator, this is in the denominator, isn't it? So C is inversely proportional to delta T. What does it mean? More the value of delta T, less is the value of C. And if delta T is less, C will be more. Okay? Since delta T is less in X, that is delta T in this case is only 3 degrees Celsius, delta T, isn't it? So lesser value of delta T means more value of C. So therefore material X has higher value of C, that is the specific heat capacity.